We recently introduced our second fundamental principle, the energy principle, where we use the total system energy E to understand and to predict motion. In particular, the principle tells us changes to the total energy, delta E, can only happen through interactions of the system with the surroundings. In the energy principle, interactions are described by processes that cause energy transfer between the system and the surroundings. Today, we'll focus on the process known as work, in which forces act to transfer energy into or out of a system. You'll recall we recently discussed an example of a system, a box, where the system energy changes, delta E, could only happen by changes to the kinetic energy, delta K. So if delta K is positive, meaning the system is moving with greater speed in the final state than in the initial state, then that meant the system gained energy. And that could only happen, according to the energy principle, if energy is transferred from the surroundings to the system. Well, one way that could happen is if someone or something gave the system a push or a pull. We're imagining here for the moment that this pull, this force we call F, is the only force acting on the box. We say that the force F is doing work W on the system. Moreover, since it's reasonable to expect that the larger the force, the more energy would be transferred, then we would expect that the work would depend on the magnitude of the force. But that's not the whole story. The work will also depend on how far the system travels while the force is applied to it. That how far is specified by the magnitude of the displacement. So the definition for work needs to include both of these ingredients. In this particular example, where the force F is in the same direction as the displacement delta R, we can write the work as the magnitude of the force times the magnitude of the displacement. We see that this expression has the dimensions of energy, so that's consistent. This expression also makes physical sense in this example. The work here is positive, meaning the force is transferring energy into the system from the surroundings. Thus, the system energy increases. Delta E is positive, which, for this specific case, means the system speeds up. The change in kinetic energy is positive. Now let's check out our expression for the work by looking at a second example, with everything being the same as in the first case, except that the force F points at an angle, theta, relative to the displacement. We would still expect energy to be transferred in, but perhaps not as much because the push isn't aligned as well with the direction that the object is moving. Our current expression for the work doesn't account for this. Let's propose this modification. Instead of using the entire magnitude of the force, how about considering just that part of the force that is aligned with the direction of the displacement, the direction the object is moving? We can visualize this by placing the arrows representing the force and the displacement tail on tail. The angle theta is then the angle between the vectors. Now the part of the force that is responsible for the energy transfer is the magnitude of F times the cosine of the angle theta. So our refined expression for work should include this, which we can write as the magnitude of the force times the magnitude of the displacement times the cosine of the angle theta. For this example, where theta is greater than 0 but less than 90 degrees, cosine theta is positive but less than 1. So the work done in this second example would be positive. Energy is transferred into the system from the surroundings, and the system speeds up. But not as much as in the first case, where the force and the displacement are aligned. Now let's try this expression for the work on this third example, which is exactly the same as the first two, except in this case the force is pointed opposite to the direction of motion, the direction of the displacement. Is the work done by the force positive, negative, or 0? Intuitively, we would expect that when F opposes the motion, points in the direction opposite to the system's displacement, then the system should slow down. So delta K, change in kinetic energy, is negative, and here, so too is the change in the system energy, delta E. By the energy principle, this means energy is transferred out of the system to the surroundings. That transfer out is negative, which means the work done is negative. Our current expression for work accounts for this. The angle between F and delta R is 180 degrees, so cosine of 180 degrees is -1, and the work done here would be negative. Notice that if the angle between the force and the displacement was at an angle between 90 and 180 degrees, the work would still be negative. The force F would still be transferring energy out of the system, but not as much as in the case where F and delta R are completely anti-aligned. Finally, consider this case. The force F is at right angles to delta R. Cosine 90 is 0, so here's a case where we have both a non-zero force, a non-zero displacement, but no energy transfer. The work done is 0, so in this case the system keeps moving at the same speed as before. The change in kinetic energy is 0. Our expression for work can be described as the multiplication of two vectors. A particular type of multiplication we call a scalar product. This is often symbolized using the dot notation. So for this reason, the scalar product is also known as the dot product. Notice that this is a kind of multiplication of two vectors which results in a number, a scalar. So let's make sure we check that we obtain scalars anytime we do a dot product. Now this expression for the scalar product is independent of our choice of coordinate system. If we have a coordinate system choice and we have F and delta R in component form, then we can find dot products using an alternative expression. Here it is. In words, what we're doing here is scalar multiplying together the corresponding components. The x component of the force multiplied by delta x, and similarly for the y and z components. And once we have those done, we simply add everything up. Remember that the result of a scalar product needs to be a scalar. It's incorrect to try to write this as a vector. Now both ways of doing the dot product give the same result. We will choose the way that better suits the problem at hand. Let's put all this together and give this problem a try. Here's how to do this. Here you need to compute the displacement, which we can do because we're given both the final and initial position vectors in component form for a particular coordinate system. Once we have the displacement, we can use the component form for computing scalar products to obtain this result. That's it for this lecture. In our next lecture, we'll work a couple of examples involving the energy principle.